Hi students, this video is about Chapter 2. And Chapter 2, the subject Chapter 2 is Kinematics in One Dimension. Alright, so the first natural question you might have is, what is kinematics? Alright, and so as I've said in the Chapter 1 lecture, we're going to, our first of two theories we're going to cover in this class is the theory of mechanics. Well, kinematics is the beginning of the theory of mechanics. And so let's define what kinematics is officially. Kinematics is the study of bodies in motion without regard as to why the motion. So this these studies were primarily performed, or the person who's really primarily responsible for kinematics is Galileo Galilei. And so, and I'll kind of explain why we're not asking the why questions yet. So Galileo, so again, chapter 2 is, the study of kinematics in one dimension. Chapter 3 will be kinematics in two dimensions, right? And so Galileo is responsible for kinematics. So kinematics is due to the work by Galileo Galilei. He lived in Italy. He's an Italian scientist and astronomer. He lived from 1564, and he died the same year that Isaac Newton was born, 1642. All right, and so what I said in the beginning of the Chapter 1 lecture is that we really are starting this class from nothing. Okay, so again, this is from Italy. Sloppy there. We're starting this class from nothing. And so Galileo was born, as I say, 1564. Well, I started, as I first said, let's kind of consider our class as starting right around 1500. And what I like to do in this class is to discuss some history of science, which I think is pertinent to kind of know. I mean, if you're taking this class, you're taking a career path to be a scientist. So the history of science, whether it's physics or anything else, is part of your legacy. And so let's kind of talk about what was going on in the world, at least in Europe, around 1500, and kind of get a perspective on Galileo and some of the things that he had to struggle with, right? And so 1500, there was, for about 1,000 years, Europe was under the rule of a very strong authoritarian Catholic Church. So for about 1,000 years, we had the Dark Ages. During the Dark Ages, there was no scientific inquiry. There was no, there was a very, very dominant power by the then Roman Catholic Church, and that was the only Christian church at that time. There was no other church, and we had rule primarily by monarchies. And so monarchies, you're born to essentially rule, and most people had nothing. Most people were serfs. They died with about as much as they had when they were born. And so this was, there's a number of bad institutions at that point in time, and it really strangled the creativity and the possible prosperity people, and of course, in the end, societies. This put, I would say, society behind 1,000 years. And so in 1439, we had, again, this goes back a little further, but we had Johannes Gutenberg, if I spell his name right, invented the printing press. With the printing press, one could mass produce, and mass publish books. And so with that, when books can be published, in a greater distribution, that means that more people were able to read, more people were able to understand, and then of course they started asking questions. So a number of changes began occurring, and again, this is 1439, not quite 1500, but by the time 1500 rolled around, a number of people started asking questions. There were questions being asked, and ideas being challenged. Okay, and so I'm kind of leading us into where physics is starting, and so people started asking questions. The printing press allowed the mass distribution of books, and really an establishment of a free press. So with that, new ideas began to emerge. By around 1500. It takes a little bit of time for printing press to get out there. It takes a little bit of time for people to write books, so a couple of, say 40, 50 years, now there's enough time for there to be a distribution of books and hence ideas. Okay? And so some of these ideas were, I would say, to question the authority of the ruling Catholic Church. So around 1517, so beginning in 1517 and lasting over 100 years was the Protestant Reformation. People began to challenge the authority of the Catholic Church. People began to say, to either challenge their authority on, on how they, basically how they rule things, or the authority of the Pope, or for instance, the interpretation of the Bible, whatever it is. There other churches began to form. The Lutheran Church began to form, and other churches began to form, and so this was met by, of course, a counter effort that the Catholic Church came up with called the Inquisition. All right, so this was really a way of trying to bat down this and beginning of weakening of their power, its power structure. Another set of ideas began forming regarding monarchies. So politically, people began questioning monarchies. Monarchies held the belief that they have the divine right of kings, and so certain ideas, some good and some bad, started to form, the seeds of ideas, the seeds of democracy and the seeds of communism began forming. None of these really took place for about another 100 years. You didn't see democracy start forming like the revolution in the United States or France until the 1700s. Because the seeds started forming. Okay, and then where we are most concerned in this class is science. People started questioning, people started having scientific inquiries. Okay, and so scientific questions began to be asked. And this is questions from, the earth is round, instead of flat. But I would say most importantly is that, the church held, so the church enforced the teachings of Aristotle. Particularly, the important, takeaway here is we have a geocentric theory. That is, the earth is the center of the universe. And of course, and you're supposed to just accept the teachings of Aristotle. All right, and so now some people began asking questions, and they started developing telescopes, and they started looking at, at evidence. They started trying to have evidence, and so the first person would be Nicholas Copernicus. Did I get his name spelled right? He provided evidence for a heliocentric theory. So the main thing he did was he says that no, the Earth is not the center of the universe. The sun is. Now, of course, we know that's not true, but it's an improvement. He was very scared because at this point in time, it was very dangerous to be a scientist. Scientists were killed. It was very dangerous to ask questions, and so being a scientist, you took a great risk and great peril. And so, in fact, Copernicus published his heliocentric theory posthumously. He was already dead. You can't kill a person who's already dead. And so Copernicus was concerned enough for his safety that he waited until he knew he was going to die before he published the theory of the heliocentric theory. Now, why is that a big deal? Again, we know the sun is, today we understand the sun is on the outer band of the Milky Way galaxy, which contains about 100 billion stars, and there's about 100 billion galaxies that each contain about 100 billion stars. So we really understand now that there's really nothing particularly special about the sun or the earth. I mean, we know that we are kind of in a mix of stars, right? But at that time, it was taught that the earth was the center of everything. Humankind was the central, most important entities in the universe. So with the heliocentric theory, we start seeing a weakening of that stance to the point where, we maybe not be so important. We're just revolving around a planet or revolving around the sun. And so that takes away some of the central importance of who we are. And then, so that's so the heliocentric theory. There's evidence for the heliocentric theory, and then comes Galileo. So what Galileo did is Galileo basically devised what we call the scientific method. Okay, and that is basically we know that scientific information is true because of verification by experiment. So sure, Galileo was a physicist and an astronomer, but this scientific method is universally applicable to all sciences. And for the first time, Galileo performed experiments. And out of his experiments developed the theory of kinematics, which is the beginning of mechanics, which we're about to talk about. So again, Galileo developed kinematics. Basically, kinematics, which is a mathematical theory of bodies in motion. Really forming the beginning or maybe we would say the structure of the true theory of mechanics. Now, I said kinematics was the study of bodies in motion without regard to why the motion. Well, it's not like Galileo wasn't concerned with why the motion. It's just he didn't know. He didn't understand. We did not know about laws of physics until Isaac Newton came about and explained the laws of physics. What Galileo did was he performed experiments to see how bodies actually moved. That is what we're going to talk about in Chapter 2 and Chapter 3. But besides kinematics, Galileo, as I said, was also an astronomer. And in fact, he actually is credited with developing a good enough telescope to be able to see and basically discover the 4 largest moons of Jupiter. So again, what are Galileo's accomplishments? Galileo basically derived kinematics. And Galileo discovered the 4 largest moons of Jupiter. And those are Io, Europa, Callisto, and Ganymede. So, what that really now tells us is that's one more level of unimportance or irrelevance that we have. Not only is the Earth not the center of everything, but we revolve around the sun. And in fact, there are celestial bodies that even revolve around other planets. So again, this just puts us one step further back. And Galileo also saw he turned to look at the moons of Jupiter. So Galileo, was somebody that was of great concern to the powers that be at that time. And the thing about Galileo, though, is he was actually very popular, very well liked. I mean, he was a man of the world. He was somebody who had very excellent social skills, kind of a glad-hander. And so even though other scientists were executed, like Giordano Bruno was executed, for stating that other stars are really suns, and that might there be other planets, maybe even intelligent life on other stars. He was burned at the stake for that statement. Kepler, in a holy war, his son and his wife were both killed. He was exiled from his home country. Johannes Kepler, we'll talk about him. And then, of course, Galileo, he ran into the powerful Catholic Church, and they did not, because he was so popular, did not want to execute Galileo. All right, and so they put him under house arrest. Galileo was basically under what was called suspicion of heresy. In fact, when Galileo died in 1642, he wasn't even afforded a regular Catholic burial. He had a very unauspicious type burial. It was because he was under suspicion of heresy for basically speaking the truth. All right, and so that's the situation that we're in, and that's the situation that scientists found themselves in the 1500s into the 1600s. All right, and so Galileo had a lot of hardships brought onto him because of the environment in which he was born in. I mean, here's the man who's the greatest Italian scientist since Da Vinci, and yet he should have had a burial with accolades, and yet he got nothing because he ran into the power structure. All right, and so that's the buildup of where we are. So let's now talk about kinematics itself. All right, and so start talking about the actual physics. Again, I'm somebody who likes to discuss the history because I think it is actually important. I think it's important to know the history of science, and since you are to become a scientist, you should know it's part of your legacy. Okay. Now, as I said, in the around 1500, we're really starting from absolutely nothing. And we want to build up this very nice theory of mechanics, the theory of bodies in motion. But we really have nothing. We have to really get down to the point where we're even defining the very terms that we're going to use, our vocabulary, nomenclature. And so it's like this. We live in my homeowner association. We live across the street from a very nice, very beautiful homes that are being developed, a community that's being developed, and we have friends of ours who live around here who actually bought into that community. And I haven't taught physics 1 since last summer, and I've been teaching primarily physics 2 for the last few semesters, and so right at the beginning of last summer, if you looked across the street at that community, all you saw was there's beautiful plans, it's going to be beautiful $1 million homes and everything else, but all you saw was a bulldozer pushing around dirt. You're eventually, after a number of methodical building operations and everything else, you're going to have a nice, beautiful set of homes. But you have to start off pushing around dirt. And so that's where we are right now. By the time we get to chapter 12, we're going to have a nice, beautiful theory, but at this point, we're just pushing around dirt. We have to define what we even should even talk about. What should we discuss in the theory? So let's kind of harken back and ask ourselves the question, what are we trying to accomplish? We're talking about a theory of objects in motion. So in the most basic sense, you need to develop a vocabulary. So the first thing you need to ask yourself is, well, I need to discuss where an object is. So again, we're getting down to the very, very basics here. We need to actually have some sort of a vocabulary to say, where is the object? Again, going down to the very, very basics. Where is the object? And so the first thing we need to do is establish a reference frame. And we refer to that as a coordinate system. So, typically, you'll see in Algebra 1 or Algebra 2, we develop a coordinate system. And usually it's, and we've been discussing this a lot with vectors, we have a coordinate system where we essentially have, plus x plus y. We have orientation in the x direction, orientation in the y direction. Now, we're talking about physics in 1 dimension in chapter 2, so our coordinate system is really going to be nothing but a one-dimensional system, really the real number line. So we establish a coordinate system, real number line. I call something that's 0, and let's say positive in one direction, negative positions in the other direction. Now, the person we have to thank for the coordinate systems that we use is a French mathematician by the name of René Descartes. So we oftentimes call the XY coordinate system Cartesian. And Cartesian means after, it's basically, after René Descartes. Okay, and so as the story goes, Cartesian. As the story goes, René Descartes was once lying on his bed. He's looking up at his ceiling and he's noticed a fly. And he asked himself the question, can I systematically characterize where this fly is located? And he came up with the idea of having the grid. X direction of a horizontal axis and a vertical axis, just like we're used to in Algebra 1. And that's a grid that's similar to maps that we see. We go to a say for instance a amusement park or maybe Disney World or something. We go in, and the first thing someone does at the front gate is they hand us a map. Let's say I want to go to Tomorrowland or something, and I looked at my map and I say, oh, that's located in F7. Okay, so I run so one dimension along the map is A, B, C, D, E, F, G, H, and the other dimension is 1 through 8, maybe. And so you run your finger along F, run your finger along 7, basically draw out perpendiculars from each of those axes, and where those perpendiculars intersect, that's where Tomorrowland is, right? And so any kind of a grid, any kind of a map that you ever use is basically an example of a Cartesian coordinate system. And that's exactly what we're gonna apply here. We need to set down a coordinate system, and everything we talk about from here on out is with respect to a reference frame. All right, and so that's the most important thing. So we need to establish a reference frame. Everything is going to be with respect to the reference frame. Okay, so the answer to my question now is, now that I have an established reference frame, and it's in one dimension right now, we're in chapter 2, we will expand to 2 dimensions in chapter 3. In one dimension, I have to specify where something is. All right, and so in so doing, I will develop what is called a position. So we'll say, let's say for instance, I have an object. I'll say it is located at +3. All right, so the object is located at +3. I will basically say, and I'll say I have a position X. Now I'll put the vector hat on, and generally speaking, for one dimension, sometimes people kind of just don't bother doing that. But essentially, I have a position X, and essentially in one dimension, my direction is only a plus or minus sign, as I've said. And again, I'm establishing my orientation as positive is to the right and negative is to the left. I will say that my position is +3. My direction is given by the sign. My magnitude is given by the size of the vector. So this is my magnitude. So position is a vector. So we refer to this as a position. It is a vector. It means it has a magnitude and a direction. So everything is going to be with respect to a coordinate system. So how would I draw this +3? Well, I would draw it as an arrow starting from the origin and going to +3. that would be my vector. That would be plus 3. Okay? If I decided instead that I want to, let's say, have a position vector of -2, well, again, let's say that's where my object is. Let's say it's not at plus 3 anymore. Now it's at -2. So what would I do? Well, I'm going to redraw my coordinate system. And instead, -2 is where my ball is, where my object is. And I would draw an arrow from the origin to +3. It's hard to see that. I mean, in 2 dimensions, what would you have? Well, I might have, object would be described as some sort of x and some sort of so much x and so much y. So I'd say, okay, maybe my object is located right there. Okay, so this is the plus x axis, -x, plus y, -y. And how would I determine this position? Well, again, my origin now in this 2-dimensional system is right where the x and y are both 0, and I would just draw an arrow from there to, and I'd call this position vector r. And that would be my position in 2 dimensions. So again, that's where I'm going to be looking. I'm going to be looking from basically every vector has got to be referenced to the coordinate system, to the origin. All right? So again, we talk about position. Position is where is the object. How can I describe the location of the object with respect to a coordinate system? Again, that is called the position. Now, and this kind of goes back to what I talked about in the first class, the first video, is I like to describe that an object has moved. So for instance, I might describe that I have an object initially at +3. And so I would say x, I'll call it x sub 0. That's kind of just usually the nomenclature, or some physicists refer to this as x naught. That's usually the way it's stated, x naught, x sub 0, and that really tells me the initial position. And so the initial position I'm going to say is it starts at +3. I have a ball, I have some marble or something that starts at +3. That is the first location of where it is. Okay, well, how would I do this? Well, I would basically say I'd draw an arrow from the origin to +3. That's my position vector. And let's say at a little bit later time, again, I'm not specifying yet how an object moves. Let's say at a little bit later time, I have x1. And I'll say that x1, the object is going to be described as being at +5. What's +5? Well, that would be a vector. Again, it's hard to draw this because it's the these vectors end up being on top of each other. It's much easier to do this in 2 dimensions. But at +5, it would be a vector that would end up starting from the origin and being up out to +5. All right, and so it would be all vectors are really related back to the origin. Now, the question I want to ask is, well, how can I characterize, this movement, this change in position? And we define, and I mentioned this last time, we define what is called the displacement. So the displacement equals change in position. That's your displacement, a change in position. So we discussed changes of something. Again, I've limited whiteboard here. So I say to change the position, I'm going to say, well, if I talk about my displacement, let's just erase this here. We're talking about where an object is. That's called position. So I have displacement. if I talk about a change in position, change means a difference. And so I would define it as x1 minus x0. And if I want to use Greek nomenclature or the actual mathematical nomenclature, I would refer to this as delta x. Okay, so delta, capital delta, is the Greek capital D. And, you know, if you want to look at what the little d looks like a little cherry, the way I draw it. And that's little delta. This is the Greek little d. Again, this is called delta. So physicists really use the alphabets of the world in defining the variables. So our 26-character alphabet, well, really it's like 52 characters if you think of capitals and small. Well, that's not enough for physicists. We have to borrow other people's alphabets. So we borrow the Greek alphabet too. And essentially, if you imagine you throw any Greek letter at me, I can usually tell you multiple things that it's used for. So again, we end up using the Greek alphabet quite a bit. So delta is a way of saying change in. So that's our displacement. Now, the positions are both vectors. We know that the addition or subtraction of vectors gives you another vector. We discussed that back in chapter 1. So we know that the displacement has got to be a vector. All right, and so let's discuss how we can calculate this. And so I said originally that x1 is positive 3, and we're still in one dimension, and x2, x0, x naught. X naught is positive 3, x1 is positive 5. So let's follow the recipe. The displacement, which is called delta x, displacement, is going to be, as I said, x1 minus x0. Now, we have to be very careful of their negative signs sometimes. Not so much here. But anyway, it's x final minus x initial. All right, so my final is going to be positive 5 minus my initial is positive 3. And this is an algebraic minus. And I find out that my displacement at this point is positive 2. Again, I have to have a magnitude and a direction. This nomenclature, this vocabulary, allows me to define how I can actually talk about not just where an object is, but actually how an object has moved. Where has it moved? I can talk about that because we know, if we look around, we know the objects move. Right? Now, as I also just talked about last time, there is a special name for the magnitude of the displacement. Remember, so displacement's a vector. The magnitude of the displacement is called the distance. In official physics term, we have displacement, we have distance. Distance is the magnitude, it's just a number. It is signless. It is the magnitude of the vector. It is as if you got a measuring tape out and you measured the size of that vector. Okay? So let me kind of give another example of a displacement. Let's imagine for a moment that kind of get a feel of what calculating displacement. So let me go back to my real number line again. Let's see, I want to go -4, -3, 2, 1, 0, 1, 2, 3, 4. call this positive x and negative x. Again, we're still in one dimension in this chapter. Let's say that I want to imagine that the initial position is at positive 3 again, right? So I'm going to start off at positive 3, whatever it is I'm watching, a ball or whatever, okay? And it ends up going to negative 4. So we'll say that x1 later is negative 4. And the question is, well, how do I describe the displacement? So again, initially, my displacement vector would be given as an arrow to positive 3. At the end, it'd be an arrow to negative 4. And so what I have to think about is, okay, well, what, again, is the displacement? The displacement is delta x, or x1 minus x0. Following the recipe, delta x is, let's be careful, final minus initial. My final is negative 4. Minus, this is the algebraic minus, the initial is positive 3. So this works out to be negative 4 minus 3, or negative 7. All right, so if I were to draw a displacement vector describing this, I mean, it would be of size 7, and it would be negative. It would be a vector literally going from, it would be going from the 3 over to the negative 4. All the way across. Right? It's a vector that's being drawn from the initial position to the final position. That's your delta vector. Now your positions are drawn from the origin, but your vector that gets changed is drawn from an initial position to the final position. Right? This is more clear when we do 2 dimensions. In 2 dimensions, I might have an initial vector, let's say over here, and we'll call this R1, and maybe the object is moving around, flying around or something, and I end up with a final vector R2. Well, my displacement is going to go from R0 to R1. It's going to basically go as a vector from R0 to R1, so it'd be something like this. Again, it would be going from, one to the other, would be the displacement vector. Again, so you'll notice that it's not being drawn from the origin. We draw from one vector to the other vector. Now, it looks a little more strange when you're confined to one dimension like we are. So again, things are going to look a lot better when we get to 2 dimensions. So it'll be easier to draw. Okay, I have another interesting question for you now. What happens if I do the following? I'm just going to kind of write this out. So, let's say, a person or a ball or an object, let's say an object. An object moves from positive x, so we'll say x initial, x naught, equal to positive 3, moves 2, we'll say 2, 3 units to the right, to positive 6, and then 3 units to the left, to positive 3 again. And the question I ask is, what is the displacement? Well, let's see. Displacement does not care about how an object moved. So we find out, well, we know initially that the object was at positive 3. Sure, it moved to the right by 3 units and back 3 units to the left. But we don't care about that because we know that at the end of the problem, it is at positive 3. That means my displacement, delta x, is going to be x1 minus x0, or positive 3 minus a positive 3, or 0. My displacement is 0. That means my distance is 0. So for this particular example, I have a distance and a displacement vector of 0. So the distance is also 0. So this seems kind of strange given that I really did travel, but that is truly the definition of the distance. It is the magnitude of the displacement vector. Displacement vector only cares about where an object started and in your analysis and where it ended. Not really what, where it went and what did it do. It's just basically a start to an end. That's what distance is. Now, that's different though. And again, I'm going over physics terms, new terms in your chapter 2. That's different than distance traveled. Distance traveled is the total distance covered by a moving object as it moves from x0 to x1, for instance. Or as it moves, we'll say delta x, whatever the displacement is. All right? It is as if it has an odometer or pedometer attached to it. In our example, it would be what? So in our example, so I'll give you a little time to write this. Now, in our example, we would be, even though the distance is 0, in this example, the distance traveled, which is also scalar, is positive 3 plus 3, or basically 6. So again, it's 3 to the right, 3 to the left. This is 3 to the right, this is 3 to the left. It's adding up all my segmented distances. It would be 6 in this case, as opposed to 0. So again, distance traveled is different than distance. They're both physics terms. Distance is, as if you had an odometer on your car or a pedometer on you, and it basically says, oh yeah, this person went 3 units to the right. Or it's basically a total of 6 units. Whereas distance would be the magnitude of the actual displacement vector, and if you end up back where you started, your displacement vector is going to be 0. Okay. So again, we're developing our vocabulary. We now have displacement, which basically we now know position. Position is where an object is located. We now have displacement, which is the difference in positions, the final position minus the initial position. We also have in our vocabulary the term for the magnitude of the displacement, which we call the distance. And we also have the term distance traveled, which I just got done covering. So all these are very important terms as we are developing kinematics. Now, as you develop kinematics, you know, Galileo looks around, he sees things in motion. And so the question is, well, they're in motion with respect to what? Again, you live in the 21st century now. You know, so many of you were born in the 21st, some of you were born in the 21st century, many of you were born in the 20th century. But in any way, you know, in our lives, we've had clocks around us all the time. You know, we understand, you know, concepts of small increments of time. Well, people back in the 1500s did not. They had an understanding of a calendar. Clearly, you know, as I wrote on the board here, Galileo was born in 1564. Well, there's an understanding of the year. You know, society, the European society or Christian society put a stake in the ground and said, we're going to call the birth of Jesus as year 0. And we're going to go and count the years since then. And so Galileo was born 1564 years later. So there is a concept of a year. There's a concept of seasons. There's a concept of a day. So these are all things. There is a concept of a periodic nature of time. And I would even say you can get even down to the second, but not in a very scientific way. And so you know, there's a number of questions you have to kind of ask. Is that it's not obvious. I mean, the time is some sort of a dimension of the universe. It's not obvious. It might be obvious to us now since we live in the times in what we live, but there's nothing obvious that time is actually a dimension. It's actually quite hard to believe. At least, I mean, I had a hard time believing it at first. I mean, when I'm a kind of person that believes things when I have proof of them. And when I took relativity theory and quantum theory, and I understood the concept of space-time, that, you know, time cannot exist without space and space cannot exist without time. And I understand, you know, the quantum theory formulas, like the uncertainty principles from Heisenberg, like what we talk about in physics too. I truly do see time as a bona fide dimension variable. And so before, I kind of wondered if it was just some sort of a convenience for us humans to kind of keep time, kind of like, you know, a drummer keeps time in a concert. You know, is this a convenience for us, or is time actually truly a dimension? Well, as it appears, it truly is a dimension. So time is the cadence variable. So time is a dimension in which everything changes. All right. So time is the dimension in accordance where objects move with respect to its change. And again, that's not obvious. If it's obvious to us, it's because we live in the times in which we live. So time is actually very well developed by NIST, National Institute of Standards and Technology, and it's actually developed. We understand it extremely well, so we can define the second very accurately. So, in fact, the second is defined. The second is the unit of time the SI unit of time and it is defined as the time required for, let's see here, 9,192,631,770 vibrations of the cesium atom. There is a state of the cesium atom that is extremely stable and repeatable, to the point where it's so repeatable that we define the second according to it. So again, it's a strange looking number, but we have a very precise definition of what a second is by NIST. They also have a precise definition of the kilogram. They also have a precise definition of the meter. You know, they do the meter via the speed of light, for instance. So we have a very precise definition for the second in the SI unit. And again, the SI unit and the English unit use the same time unit for called the second. All right. Now, we need to increase our physics vocabulary. If we understand that objects move with respect to a change in time, then we need to start developing nomenclature that discusses this. And so we develop a concept called the velocity. So the velocity, well, let's see what we would think that the velocity might be, and see if we have to fix the definition. So the velocity, we'll say, is the change in position with respect to time. Okay, and so we might say that that's going to be some sort of an x final minus x initial divided by t final, you know, basically the time in which the object was at x1 minus the time t0 in which the object was located at x0. Okay, we would define that as the velocity. Now, the question is that good? Is that a good definition of velocity? Is that an operational definition? Well, let's see. Let's kind of give an example. So let's say, for instance, that I'm at my main job at Raytheon, and it's about 5:30 in the afternoon. I'm in Dallas, and somebody times me, and they say, "Oh, okay, well, it is T0, T sub 0, and we'll say it's 5:30 p.m. Okay? And let's say I drive, and let's say for nice numbers, it's 20 miles for me to go from Dallas over to Fort Worth to basically arrive at school. And I have somebody with a stopwatch at the school's parking lot, and they say, aha, you are here, and it is now exactly 6 p.m. And I have traveled delta x of 20 miles. As my example. So the question is, well, what's my velocity in accordance with this definition? Well, we would say that my velocity is going to be 20 miles, and I'll just take the hat off. Velocity is a vector because I have a vector displacement divided by a scalar. We know a vector divided by a scalar is a vector, right? So I'm going to just worry about the magnitude of velocity, and I'll talk about that in a moment. It's actually called speed. But let's just say I have 20 miles per hour divided by half an hour. So we would be saying that I would be traveling at 40 miles per hour. Is that true? Well, truly I was not traveling 40 miles per hour in the parking lot. That's not true. That would be dangerous. I wouldn't do that. So I wasn't traveling 40 miles per hour in the parking lot, and I wouldn't be traveling 40 miles per hour in the freeway either. And so no, that I might not have traveled at 40 miles per hour ever. I mean, if I'm going, let's say, 70 or 75 miles per hour in the freeway, then my speedometer has gone through 40 miles per hour, but I may have not ever actually had an appreciable amount of time at 40 miles per hour. What we come to find out is that this definition, as given, is usually what we refer to as the average velocity. I put a bar on top to say this is really the average velocity. Now, it's kind of like if I took your exam 1 scores, and let's say, all my exam 1 scores, I have 10 questions, each question's worth 10 points, so, and I don't give fractional credit, so you're going to get integer answers, 8 out of 10, 9 out of 10, 10 out of 10 for any given questions you have, and so you're going to have some sort of a integer value. Let's say, for instance, I add up everybody's score and I get 74.3. Well, clearly nobody in the class got a 74.3. It's very well maybe nobody in the class even got a 74. But for some reason, that is the average that we get. So it's the same kind of thing. This is an average velocity. So how do I improve this definition? Well, let's say I want to find the velocity at some point. Let's say I want to find a velocity. Let's improve the definition. We improve the definition by reducing delta t. Okay, let's pick a smaller time differential. So instead, I'll say, well, how about you want to find my velocity crossing a road sign on the freeway? So let's say, time me 100 yards before and after a road sign. For instance. Well, okay, that's going to be better. If you're interested in what my velocity is crossing the crossing a particular road sign, having delta t, whatever time it took me to go, basically a grand total of 200 yards, that's going to be better, but that's still an average velocity. I may have put my brakes on. I may have accelerated. So you're still not really getting it. So what do you want to do? You'll reduce delta t some more. And some more. And eventually, to really do a perfect job, you want to reduce delta t to be so small as to be infinitesimal. If you want the instantaneous velocity, we really got to make delta t as small as can be, even approaching 0. So we would say instantaneous velocity, we would say in mathematical nomenclature, we would say it's the limit as delta t approaches 0 of delta x over delta t. And what we have just got done defining here is the definition of what is called a calculus first derivative. So you're now doing differential calculus. And so you would change out the deltas for little d's. You would say this would be dx dt. This is a first time derivative. And you're doing calculus 1. Okay, and I've said, that I try to tell you where you're missing out by not having calculus. Already, we're only in chapter 1, and on the beginning definitions of kinematics, we're already discovering that there's going to be a discrepancy between how we do physics and how physics is really done. If you really want to find out what the velocity is right now, you need to employ the instantaneous slope. Or I haven't talked about slopes yet, but you need to make your delta t be what's called infinitesimal. So when you do this, delta t is what we call infinitesimal. Now, we're not doing calculus in this class, and so, but I want to kind of tell you what you're missing. All right, and so, well, let's just kind of harken back a little bit and say, okay, well, what happens though if I do have a constant velocity? I mean, clearly I didn't have a constant velocity in my example with the driving from Dallas to Fort Worth. But let's kind of make an assumption that, let's say I do have a constant velocity for a moment. Okay, so now let's assume that I do have a constant velocity. So now assume a constant velocity. Again, this is a special case. Velocities are generally not constant. You know, as you can see, as you drive your car, you're going at different velocities. But we're going to make an assumption. We're going to kind of just look at a special case. So essentially a constant velocity, and what I like to typically do is graph it with respect to time. So I like to generally say, okay, well, I'm going to look at a graph, and it's going to be a two-dimensional graph, and it's going to be the position versus the time. I have time on the horizontal axis, and I have the position. I'll just take the hats off the variables right now. And again, I'm talking about one dimension. All right, and so I'm talking about constant velocity. Let's just say, for instance, let the velocity be 5 meters per second, just a constant number. Okay, now the question is, okay, in the very beginning, at say t equals 0, well, again, what is this graph showing? Well, the graph is showing is when we're talking about a one-dimensional problem. And so if we're going from 0, let's say an object's going away from you, going to 0, it's going further and further away from the origin as time progresses. This x is basically saying, the object starting at the origin, it's going further and further and further away as time progresses. And the horizontal axis is the time. So let's say the object is at x equals 0, it's at its origin at t equals 0. So I can put a point right there. And now, let's say at, let's say at 5 seconds, I would be how far? Well, in 5 seconds, if the object is going 5 meters per second, it'd be 5 times 5 or 25, right? And so I'd be up here at 25 meters away. I mean, it's going at a constant 5 seconds. I mean, I'd have 5 meters, basically 5 of those increments. In 5 seconds, it's going to be 5 meters, 25 meters away from me, or 25 meters away from the origin. And let's pick another point, let's say at 10 seconds. Well, 10 seconds, again, it would be 50 meters away. Let's say this is in meters. And now we're at 50 meters. And essentially what you can look at here is you can see that you're in a line. You're forming a line. When you have a constant velocity, the position time graph is linear. Okay? So for a constant velocity, the position time graph is linear. Linear means that it is in a line. That basically, you're not going to have any curves in this plot. It is a line. All right? So we can actually use the algebra that we know. So I go back to algebra 1. And I say, okay, in algebra 1, we always talked about x-axis and y-axis. Now, we've been talking about this in this class so far. And let's go back and discuss the equation of line. Let's just say we have some sort of a line. All right, and so back in the equation of a line, if you remember, equation of line is y equals mx plus b. That's the equation of a line. Again, I'm going back to algebra. Okay? Again, we're going back to Algebra 1 for a moment. All right? So, equation of a line, y equals mx plus b. Remember, b was the y-intercept. B is, the location along the y-axis of which the graph crosses the axis. M is the slope. Now, in the case where the line goes through the origin, then b would be 0. So let's consider that case. Let's imagine the case where the line goes through the origin. All right, in that case, b is 0. Okay, what is m? How do you figure out m? All right, so what you have now is y equals mx. If b is 0, you have y equals mx. Now the question is, if your algebra teacher asks you, how do you find m? Well, what do? Well, you have 2 points on a line. So you have one point that we would refer to as x1, y1. Another point, x2, y2. All right, and so if you want to find the slope, what do? Well, you basically say that slope is the change in y over the change in x. y2 minus y1 over x2 minus x1. Or delta y over delta x. Oh, this is looking familiar. Delta y over delta x. Well, let's just kind of imagine here that I take this information and I go back to physics. And in physics, I have what? I have a t1 x1. This first point. The second point, I have a I'll say a t2 x2. And I have a line. I have y equals mx type of relationship. Well, how do I find my slope? The same way, right? And so let's kind of erase this. I'm gonna employ the Algebra 1 concept here and say, I want to find the slope of this line. How do I do it? Well, I take the change in the vertical coordinate. In this case, it's x. x2 minus x1 divided by the change in the horizontal component. In that case, it's the time. t2 minus t1. Or delta x over delta t. And we know that from our definition that is the velocity. The velocity is the slope of the position-time curve. Okay? And so if you have a situation where the velocity is constant, then it doesn't really matter. Your definition, the initial definition that I gave you, is perfectly fine. Because if the velocity is constant, the average is going to be the same as the constant value. I mean, if I take the average of 10, 10, 10, 10, 10, for instance, I have 5 values that are each 10, well, the average is going to be 10, right? So the average velocity is the instantaneous velocity in the case of a constant velocity. So in the case of a constant velocity, my initial definition is perfectly fine. But what happens, though, if you have a situation looking like the following? So let's say instead of a linear plot, let's say I have a more realistic situation. Let's say instead I have a position-time curve that's maybe like a parabola. And I want to find out, well, what's the slope, let's say, or what's the velocity, let's say right here. I'm just going to pick a special spot, t0, and I say, okay, well, let's apply the formula here, and let's figure out what the velocity is. And so let's say I'll just say, well, I'll just pick, I don't know, well, we'll call this t prime. All right. We'll say I have t0 and t1. I pick 2 points along here, and I say, all right, let's apply this formula. The velocity is, delta x over delta t. And it is what? It's, say that this is going to be some x1 and this is some x0, just for grins. So I have x0 minus x1 minus x0 divided by t1 minus t0. What have I done? Well, I've essentially described a calculation that's really a line extending from x0 to x1. And I'm losing all this information right here. And so this is it's going to give me a very wrong answer. How do I fix that? Well, I pick a smaller delta t. So maybe instead I'll say, all right, well, let's pick a delta t that's smaller. So I'm just going to kind of fix this up a little bit, and I'll say, oh, well, I still am interested in t prime. Let's pick a delta t where I'm getting closer and closer. Maybe this is my t0, and maybe this is my t1. And essentially what I really want to get is the tangent line at that point. I'll still not quite get it. What I really need to do is, as I said before, I need to consider my delta t to be so skinny. And I take the limit as delta t approaches 0 of delta x over delta t, and that we know is the first derivative of calculus, the first derivative of position with respect to time. And I'm not expecting you to understand calculus, but again, what is this? Officially, it is the first time derivative of the position. And that's actually what you need to be able to do this problem. Now, we're going to, in a clever way, avoid this, but I'm just telling you what you're missing. All right? You really want to find the instantaneous velocity. In order for you to do that, you have to be able to consider the delta definition down to the point where you're considering infinitesimal deltas. Okay? And so, now that's the velocity. Now the velocity there's a special name for the magnitude of the velocity. So as we know, there's a special name for the magnitude of the position. We call or the displacement, we call that the distance. Well, the magnitude of the velocity is called the speed. So notice when you go on the road, you don't see velocity limit signs, you see speed limit signs. Because some smart aleck like myself could tell the officer, say, well, officer, what direction is this law apply? There's a velocity limit. Okay, well, does it apply along this northbound on the highway, or is it eastbound, or is it southbound, or how does it apply? Well, there is no question because it's the speed. It doesn't matter. The speed basically means that I have the magnitude of my velocity vector was greater than a certain amount, and it doesn't matter what direction I'm going, I'm getting a ticket, right? And so the idea is that the sign is very carefully labeled as a speed limit, so that it doesn't matter what direction you happen to be going. If if the magnitude of your velocity has exceeded a certain value, then you get a ticket or you get talked to. All right, and so that's we've seen these variables in our lives, but again, these didn't exist at the time of Galileo. All right, now the next variable we want to talk about is the as I know. In my example, from driving from Dallas to Fort Worth, clearly my velocity changed. So we have a variable that discusses the change in velocity. So we call that the acceleration. The acceleration is defined as the change in velocity with respect to time. Again, a lot of what I just got done talking about is the same. I mean, the acceleration, just like the velocity is the slope of the position time curve. The acceleration is the slope of the velocity time curve. Okay, and so there's a lot of change in it. And so again, this definition gives you an average acceleration. And so if you really want to do it right, you'd want to consider delta t to be so small, again, as to be infinitesimal. So if you really want to talk about an instantaneous acceleration, again, this is deja vu here. You would say the acceleration is really the limits as delta t approaches 0 of delta v with respect to t, the change in the velocity with respect to time, and we would use calculus notation. We refer to that as dv dt. It would be the first time derivative of the velocity. And, well, we can actually make a little bit of a variable combination at this point. Again, this is our class is not officially a calculus class, but let's just kind of imagine for a moment. You'll see this nomenclature briefly from me. I try to give the notions of calculus. When I talk about vibrating objects, I'm going to need to discuss this nomenclature I'm about to give you. So we just got done talking about that the instantaneous velocity was the time rate of change of the position. Basically, a fancy way of saying the instantaneous slope of the position. We also got done saying that the acceleration is the time rate of change, or the first derivative of the velocity. So I know the velocity, so why don't I substitute for the velocity? And I can actually write the acceleration in a special nomenclature. I can say that the acceleration is the second time derivative of the position. We would say the acceleration is the second order, or the second time derivative of the position. Basically, it's the slope of the slope. Slopes, I guess I would call it, of the position time curve. It is a second order slope, if that makes any sense. So essentially, the velocity is how the position changes in time. The acceleration is how the velocity changes in time, or it is the slope of the position with respect to time. All right, it's a second order time rate of change. All right, and so that's what the acceleration is. Now, that's maybe over, a little bit complicated seeming, but again, we're going to make an assumption at this point. Okay, so we're going to make a very large, very important assumption. We're going to assume that the acceleration is constant. In all future problems. Now you might say, well, is that a good assumption, or am I losing generality? Well, it becomes a little bit more comfortable when you talk about Newton's second law. So again, we don't know Newton's second law yet, but Newton's second law says that there's a relationship between force and acceleration. So this is force equals mass times acceleration. And so I can imagine applying a constant force over a period of time. And so I can imagine applying a constant acceleration as well. So it's not such a bad assumption. And in fact, physics actually works very, very well with the assumption of a constant acceleration. Okay, so what does that do for us? Well, what we're going to do is we're going to derive equations for constant acceleration. Okay, and so making a constant acceleration assumption, let us first imagine here that we're going to start off, I'm going to basically derive a toolbox of formulas that are going to allow us to predict motion. We're going to actually develop a way of doing two-dimensional kinematics. And again, we're going to assume constant acceleration. That's very important here. Now, let's start off, do a little bit of math here. Let's start off again with our concept of the average velocity. We said that that's the time rate of change of the position with respect to time. So what can we say? Again, that's the average. So again, I'm going back to the average. I'm not employing calculus. Because again, I'm talking about an average. That overbar, this overbar means average. This is an average velocity. Remember, with an average, we don't have to discuss an overbar. So what does this mean? Well, this means that we're going to talk about x1 minus x0 over t1 minus, or we'll just actually set it, we'll say that the x right now, we won't put an x here, we'll say the x right now, the final x is, we'll just call it x, the initial x we'll call x naught. And then the t right now we'll call it t0. All right, so again, instead of x1, I'm just going to say x. You know, basically, that's the x right now. Your initial x, we'll call it x naught. Your time right now is t. Your initial time is t naught. Now, without loss of generality, we can just assume that t naught is 0. All right, that just basically means that I'm starting the stopwatch for the problem at 0. I mean, again, no loss of generality. It's perfectly okay to say that. Let's also understand, so what V is. Well, again, V is going to be, again, if you take an average, it's really going to be the sum of the final speed and the initial speed divided by 2. You know, like if I take, average, let's say 10 test scores, what do? I add them all up and I divide by 10. I have two velocities that I'm considering here, the final and the initial. What's the average velocity? Well, I add the two up and I divide by the number of them, that's 2. Okay, so I'm going to fix this equation by basically saying, okay, well, what I have up here is I now have that V bar is x minus x naught divided by t. That's my V, because I just told you that t naught is 0. And then I can do is I can cross multiply and I can say x minus x naught is v bar t. Again, all I'm doing is cross multiplying, and I can say finally that x minus x naught is v naught plus v divided by 2 multiplied by t. This is my first kinematic equation for constant acceleration. Okay, I'm going to put it up here on. I'm going to try to collect these on the side here, which I'm real estate challenged here. So again, what did I say? I started with the definition of the average velocity. I made a couple of assumptions. I specified what the average velocity is. I made an assumption that I'm going to start my stopwatch at 0. And so what I just did is I rewrote the equations. V bar is now x minus x naught divided by t. T0 is gone. And I cross multiplied. I get x minus x naught equals v bar t. And then I wrote out what v bar is. Okay, so that's all I did. I'm going to erase that. I'm going to try to collect my equations as I derive them in a little parking lot here if I can. All right, so my first, again, I'm assuming acceleration is constant. With that assumption, I have my first kinematic equation. X minus x naught is v naught plus v divided by 2. All multiplied by the time. Okay, that's going to tell me is that I essentially, if I basically, hopefully I know all these variables except one, and I can use this equation to govern where where the object is going to move. I can predict where another the value of another variable, the next value. Okay, you'll see this. This will make more sense as we progress. Right. So I know this equation so far. Okay, I'm going to just kind of leave it there. All right. Now the next assumption I'm going to make is I'm going to go back to the definition of acceleration, and basically this is the average acceleration. But since the acceleration is constant, the average of a constant is just the constant. So really what I have here is the instantaneous acceleration. So this is really the instantaneous acceleration because the acceleration is constant. So A is instantaneous since we assume that it is a constant. All right, and then I'm also going to make the assumption, so what I have here is A is delta V is V minus V naught divided by T minus T naught. That's what it is. I am again going to say that my stopwatch starts at 0. That means that I can write that A is V minus V naught divided by the time. And I just need to flip it about the equal sign and cross multiply. And I can say that V equals V naught plus A T. All right, and so what did I do? I multiplied by T, I added V naught, and I flipped the equation around. So again, you can do this, but this is the second kinematic equation. V equals V naught plus AT. So again, every kinematic equation has one of the major variables missing. This one has A missing. This one has the x minus x naught or the displacement missing. All right, and so again, you use one equation versus another depending upon what you know in your problem. All right, so I have now 2 kinematic equations in my toolbox. I'm going to try to collect them on the side here. May not be easy to do. There's one kinematic equation. The next one is V equals V naught plus A T. All right. Now, what I'm going to do at this point is I'm now going to combine both of these kinematic equations and try to come up with another one. And so what I'm going to do instead is I'm going to now take a look at this equation here, and I'm going to essentially play a little game. I'm gonna add v naught to both sides. And nobody says that I can't do that. I can add whatever I want to either side of an equation. So I'm going to take this equation, and I'm going to just add v naught. V naught plus v. No, v naught plus v naught is 2v naught plus at. I mean, what I add to the right, what I add to the left, I can add to the right. Again, you may wonder, why am I doing this? Well, I'll tell you why in a moment. What I'm trying to do is I'm trying to create this so I can substitute. Okay, so what do I need? I got v naught plus v. I need v naught plus v divided by 2. So what am I going to do? I'm going to divide both sides by 2. All right, and so what I have here now is v naught plus v over 2. 2v naught over 2, that's just going to be v naught plus 1/2 at. Again, all I have done is taken this second equation, I added v naught to each side, and I divided both sides by 2 and rewrote it. Now what am I going to do? I'm going to actually substitute into here. Okay? And what am I really doing? I'm trying to basically eliminate the final velocity as my variable now. I'm trying to create another equation where the variable that I don't see is the final velocity. All right, so in so doing, once I make that substitution, I have that x minus x naught equals, instead of v naught plus v over 2, I'll put its equivalent that I just got done deriving. So instead, in that parentheses, I will substitute v naught plus 1/2 at, and then I still have this t over here. So all I did is I substituted for the equivalent expression for v naught plus v over 2. I put right into there, and now all I have to do is kind of clean it up. So now I have x minus x naught. Distribute the t equals v naught t plus 1/2 at squared. That is my next kinematic equation. That's a kinematic equation where the variable that's missing is the final velocity. Okay? And so I've just got done deriving that. I'll now stick that on my list of equations. All right? So I'll give you a little moment to copy this. All right, I'm going to get rid of this little arrow. Try to put some sort of pristine order back into this. And I'm just going to basically write this equation here. So my third equation that I'm going to use now adding to my toolbox is x minus x naught equals v naught t plus 1/2 at squared. All right, that is, that's my third equation. I'm going to derive one more equation for my kinematic equations. All right, and so what I'm going to do in deriving that is I'm going to essentially combine. I'm going to eliminate the time between this last equation I just got done deriving and this previous equation. Okay, so what I'm going to do here is I'm going to write this equation out. Now, let me kind of start it. Let me take this equation first. All right, and I'm going to take this equation and I'm going to rewrite it, but I'm going to solve for the time. All right, so basically, in so doing, what am I going to do? Well, I have to kind of conserve space here. So I want to solve for the time. So I'm going to subtract v naught from each side and divide by a. So I'm going to take this equation, rewrite it as t equals v minus v naught divided by a. What did I do? I subtracted v naught and I divided by a to get t by itself. And then what do I want to do? Well, at this point, I want to substitute for t here and here. I want to eliminate time as the variable now. I want to have an equation where time is not present. All right, so if I do this, I get x minus x naught is v naught. I don't want to put t. I want to put its equivalent. which is v minus v naught over a. Okay? And then I want to add 1/2 a, and then t squared, put the equivalent in here. V minus v naught over a quantity squared. And so what I did is I rewrote, I basically expressed time as a function of everything else. I solved for time, and I eliminated. You basically have two equations. You want to eliminate a variable. You solve, you basically solve one for the time, one for, solve for the variable, and then you substitute it in. So I basically solved for time, v minus v naught over a, and I substituted into each of these times. All right, so this is what I have now. All right, so now I'm going to clean it up. All right, so I have x minus x naught is v naught v divided by a. V naught minus v naught squared over a. All right, and then I gotta square this thing out. So plus 1/2 a. Now, squaring this thing out, I'm gonna have an a over an a squared on the bottom. So I'm basically just gonna have a left on the bottom, right? I have an a on top and an a squared on the bottom. That's the easy square. A divided by a squared is just a left on the bottom. However, I still have to square out this up. I got to use FOIL. So v squared, okay, v times negative v naught is negative v naught v, and then negative v naught times v is negative 2 v naught v, and FOIL. And then I have the last one, positive v naught squared. All right, and so I'm going to clean it all up, and I find out that x minus x naught is v naught v over a minus v naught squared over a. Okay, I have v squared over 2a. Now this 2 and this 2 cancel, so I have again a minus v naught v over a. And then finally, I have a plus v naught squared over 2a. And at this point in time, you hope that something cancels. And yea, verily, yes, this term and this term cancel each other out. All right, and so, and then on the other hand here, I can play a little game. I can say, well, I have this v naught squared over a. Well, I've multiplied by 2 over 2. I can say that this is 2 v naught squared over 2a. All right, and so again, I need to get a common denominator. I have this one and this one over here, so I need a common denominator. So what I can do is next write out. Okay, I need to substitute, or I need to erase. Okay, we're almost done. So what I now have is x minus x naught equals, all right, I have negative 2 v naught squared over 2a, and I have basically positive v naught squared over 2a. So I'm going to have basically negative 2 plus 1 is going to give me a negative 1. So I have, combining these two, I have negative v naught squared over 2a. And then the only thing left is this one plus v squared over 2a. All right. I'm going to multiply both sides by 2a. Okay, if I multiply the left by 2a, I get 2a x minus x naught. On the right, all I do is clear out the denominator. So that's going to be v squared minus v naught squared. And I just have one more line of algebra. And I can essentially put the v naught squared on the side, and I have that v squared equals v naught squared plus 2a x minus x naught. And that is the last of the kinematic equations. All right, so I can add this to my list. All right, and so adding this to my list, I now have, let me get rid of all these arrows now. I have to do very clever algebra now that I have a very limited whiteboard. All right, so my last equation is v squared equals v naught squared plus 2a times x minus x naught. Okay, I have now derived all of the kinematic equations that we're going to use in the one-dimensional physics, and honestly, really, quite frankly, for the two-dimensional as well. When we, make more sense when we talk about two dimensions. But this is my toolbox. So essentially, what I have to do is I have to look at this and say, okay, well, the idea is we have, what are the variables that we have? Well, the variables that we have is the displacement. All right, what other variable comes into play? We have the initial velocity, v naught. We have the final velocity, v. We have the acceleration, a. And we have the time, t. That's basically x minus x naught is considered a displacement. That's one variable. So this is generally considered the displacement. All right, that's one variable. But so we have 1, 2, 3, 4, 5 variables. Well, notice that every single equation up here is missing a variable altogether. All right, so the top equation is entirely missing the acceleration. The acceleration does not come into play whatsoever. The other variables are present. The second equation, it's entirely missing the displacement. Doesn't even come into play. The third equation is entirely missing the final velocity. And the last equation is entirely missing the time. All right, and so you hope that out of these 5 variables, you know 3 of them. One of them, you pick the equation that doesn't involve it whatsoever, and you solve for the other variable that you're looking for, that you're trying to solve for. So again, you hope that you know at least 3 of these 5 variables already, and that essentially you can ignore one and solve for the other. So again, you pick the right equation. So the idea is you get a problem, and then you pick the equation you're going to go use to solve the problem. So this is your catalog. These are the equations you need to choose from, and which equation you want to use to solve the problem. All right. And so let's at this point let's discuss. Actually, I'm going to discuss one more thing, and then we'll do some problems. All right. So again, these are the equations that we want. Now, one really, as I kind of told you, is do you really have any good examples of constant acceleration problems? Well, we know that if a force is applied over a good period of time, a constant force, that we would have a constant acceleration problem. But one good natural constant acceleration is the acceleration of gravity. So all bodies. So basically, in a vacuum, all bodies, Galileo was the first person to show this, all bodies fall to the earth at a constant acceleration. And we take it to be, in this class, we take it to be g equals 9.80 meters per second squared. I will prove in chapter 4 why the Earth has 9.80 meters per second squared. Other planets, moons have different values. But for right now, we're not going to worry about that. Galileo had no idea. But he did know that the acceleration of gravity was, is basically this value. Now, it turns out that if the Earth was a perfect sphere and uniform in its density, that there would be a constant acceleration everywhere. But the Earth is not a perfect sphere; is actually oblate spheroid, and so it's actually fatter near the equator than it is at the poles. And I'll explain why that is when we get to the appropriate chapter. So what that basically means is that G varies a little bit depending upon where you are on the Earth. In this class, we're going to assume a spherical Earth, and we're going to assume that G is 9.80 meters per second squared. But what does this mean, though? This is not a variable. You know, the acceleration is set to be this particular value. G is actually a particular value. Even though it looks like a variable, when you say G, you are really talking about whatever the gravitational acceleration of the whatever planet or moon that you happen to be on. So what does that do for my equations I just derived? Well, what you want to do is you want to make an assumption. And so you want to, instead of we've been talking about horizontal motion all the time, but this works perfectly well in vertical motion. It turns out that gravity operates vertically. And so you'd have to go and have an axis that is vertical and just really talk about y. So I'll just imagine for the moment I have plus y and minus y. And so my variables, you know, I might have an initial velocity of a ball. Maybe the initial velocity is up. And then it goes up and it comes back down. Gravity is going to be down. So, and then I might have, you know, different values of y. Maybe the ball starts at y naught, and maybe I'm looking at it later on at some value of y. So the equations I just got done deriving are going to change a little bit. Instead of the variable x, I'll use the variable y, with the assumption that gravity is in the negative direction. So my variables would look instead, you know, instead of my x, I would have y equals y naught plus v bar times t. Again, or let's be more accurate. I mean, it looks very similar. V naught plus v divided by 2 times t. Again, that's the first equation that I derived. All I really have to change, so again, that equation does not have the acceleration in it. So it doesn't really care about gravity at all. The only thing I have to actually change are the variables from x's to y's, the vertical variables. All right. My next equation, that's going to look like v equals v naught minus gt. So and understanding that my v's are in the y direction. My v's are up or down. Okay, so again, v and v naught are along y. Okay, so keep that in mind. They're not any way along x. They are along the y coordinate now. Okay, but again, what does negative g mean? Now, negative g basically means that the acceleration is always down. Gravity always wants to accelerate objects toward the Earth. It's always going to be acting down. Again, acceleration is a vector. So again, it does have a direction, and that direction is always down. What's the other one I had? Well, I have y minus y naught equals v naught t minus now 1/2 gt squared. It used to look like plus 1/2 at squared. But remember, a is equal to negative g. It is now specific. So this is no longer even a variable. It looks like a variable because it's a letter. This is a value. That value on Earth means 9.80. That is not a variable. All right, so we have one out of all those 5 variables I told you about. We have one less variable now. We only have 4. We're talking about, this is called freefall. You're talking about freefall. You reduce your number of variables by 1 because you know exactly what the acceleration is. And then the final equation I derived was v squared equals v naught squared. And again, I used to say plus 2a x minus x naught. Now it's going to be minus 2g y minus y naught. So again, I changed the x's to y's. If you look at what you previously wrote, I changed the a, the positive a, to a negative g. So those are the kinematic equations for free fall, for an object moving in gravity, in a gravitational field, a constant gravitational acceleration. All right. What's left to do at this point is I'm just going to go and work out some problems. All right. And so I tried to work a lot of problems out. There's a lot to be discussed in this chapter. And so let's do a few problems, and I'll call this video done. So as a first problem, again, I'm going to look at open. When I say OS, I mean open stacks. That's that. Again, that's that first book that I showed you. So open stacks. Again, you would derive it off of the Rice University website. Again, this is not the book for this class, but this is a book that I've worked a lot of good problems. There's a lot of good problems in this book, and so I typically will lean on this book. So when I put OS, it means I got the problem out of OpenStax. And so I'm going to look at OpenStax 2.41. Again, what does that mean in my nomenclature? It means Chapter 2, Problem 41. That's what that means. All right. And so what this says is it says calculate the displacement and velocity at times A 0.500 seconds, at a B, which is 1.00 seconds. C is 1.50 seconds. And D is 2.00 seconds. For a ball thrown straight up with an initial velocity of 15 meters per second. Initial velocity, 15.0 meters per second. All right, so there's a lot of information in this problem. This problem is going to be a little bit painful to do, but what this problem kind of shows you is how the object, essentially when the object is getting thrown upward, it's going to have its initial velocity be the largest velocity it's going to experience, and it's going to slow down. And it's going to, because of negative acceleration, so the velocities are going to eventually get to a maximum value of 0. And then it's going to start coming down again and accelerating downward. Okay, so we're going to try to see how this works. And so, again, note down what times we're talking about. I want to erase a lot of this stuff. But again, we're looking for the displacement and the velocity at various times, these times, all right? And the important thing is to understand that the initial velocity, the velocity of the ball first experiences at time t equals 0 is 15 meters per second upward. Okay, that's very important to keep in mind. Gravity is working downward. The initial velocity is working upward. So what I expect to see is I expect the initial velocity to be the largest at t equals 0, and then eventually reduced down to 0, and then I would expect to see the displacement. I would start seeing y minus y naught be downward, and I expect the velocity, or actually I expect y to reduce and the velocity to be negative. All right, so let's see how this works out. And so what equations am I going to use? Well, I'm going to use y minus y naught equals v naught t minus 1/2 gt squared to predict my y as a function of time. And to predict my velocity, I'm going to use v equals v naught minus gt. Those are the equations I'm going to use in time to predict what's happening. All right, and so I'm going to start off by saying, okay, let's look at A. Let's let t equal 0.50 seconds, all right? And so if I do that, I realize here that I'm being told that, that I can define y naught however I wish. So I can define y naught, I can say that y naught's initial position, I can call that 0 without loss of generality. I can just basically say that this ball is being thrown from y naught equals 0. It doesn't matter. And then all I have to really worry about is what y. So I can actually make this a little simpler by just declaring that y naught is 0. All right, and I'm free to do that. I'm free to basically say that where this ball's thrown is 0. It's 0 on my vertical. All right, so what this is going to be is that if I put t equals 0, I know constantly that v is a positive 15 meters per second. I know that. And so my y will be 15.0 meters per second times, again, I'm asking about half a second, 0.500 seconds, minus 1/2, 9.80 meters per second squared, times, again, it's going to be 0.500 seconds. Don't forget to square that. This last item is squared. When you go and do this calculation, you will find out that your y at t equals 1/2 second is going to be 6.28 meters. So you've gone from y equals 0 to 6.28 meters in 1/2 second. What about the velocity? Well, the velocity is going to be the initial velocity, 15.0 meters per second, minus 9.80 meters per second squared times 1/2 second. And again, that's just to the first power. And if you work this out, you find out that the velocity, you find out that the ball slowed down a little bit. And you work this out, you realize instead of going 15 meters per second, 1/2 second later is at positive 10.1 meters per second. So it's not going as fast any longer. All right, so what I'm going to do is I'm going to kind of remember how I'm doing these. I'm going to kind of keep track of my results. I'm going to kind of track my results to the side here. So I'm going to kind of just track the results and say, where am I? I'll do a y and I'll do a v. So what I just got done figuring out here is that, and again, I'll do a t. So we're down 0.5 seconds. My y is 6.28. Y is in meters. My velocity is in meters per second. And my velocity is going to be 10.1. Okay, so again, that's where I am right now. Okay, I've gone up, again, we're talking about 1/2 second. And y has gone to 6.28 meters. All right. So we're going to assume this is meters per second. All right. So that's at t equals 1/2 second. At t equals 0, I was at 0. Okay. So let me do one better. Sorry. Let me say that at t equals 0, y was 0. The velocity was 15 meters per second. Now, 1/2 second later, 0.50. I'm at 6.28, and the velocity has now been slowed down to 10.1. All right, so that's where I am now. All right, what about t equals 1 second? All right, so t equals 1 second. Moving on, so let's let t equal to 1. Okay, what about my position? Y equals v naught t minus 1/2 gt squared. All right. Y, remember v naught's 15 meters per second times 1.00 seconds minus 1/2 times 9.80 meters per second squared times 1.00 seconds squared. Again, that 1 is squared, but who cares? It's just 1. If I work all this stuff out, 15 times 1 minus 1/2 times 9.8 times 1 squared. If I work this out, I come to find out that y becomes 10.1 meters. So y at t equals 1.00 seconds is now 10.1 meters. So I started at 0 at 1 second. I have now gone to 10.1. So I jumped from 0 to, I went from 0 to 6.28, basically a difference of 6, and 6.2 to a difference of around 4. Now in the second half a second. So again, I'm not climbing as fast. What about the velocity? The velocity is going to be v naught minus gt, same equation. V is going to be 15 meters per second minus 9.80 meters per second squared. Again, I'm at 1 second. If I work that math out, the v at t equals 1.00 seconds, my velocity has now slowed down to 5.20 meters per second. So I've slowed down quite a bit. I've gone from 15 meters per second at t equals 0, half a second later, I've slowed down to 10.1 meters per second, and a half a second later, I'm down to 5.20. Given that these velocities are still positive, that means I am still rising. All right, so we want to do 2 more of these variations here. So we're basically kind of tracking the rising ball. All right, and so the next one is t equals at 1.5 seconds. Okay, so what do? Well, I go y is v naught t minus 1/2 gt squared. Y is, again, the initial velocity is 15 meters per second times 1.50 seconds minus 1/2 times 9.80 meters per second squared times 1.50 seconds quantity squared. Again, be careful here. You got to square this, multiply by 9.8, multiply by 1/2. Make sure it's negative. All right, and so if I do that, I find that y at t equals 1.50 seconds is going to be at 11.48 meters. If I do so again, I'm not climbing anywhere near as fast. All right, and if I look and I say, well, what about the velocity? Well, the velocity will be v naught minus gt. The velocity will be 15.0 meters per second minus 9.80 meters per second squared times 1.50 seconds. I will find out that my velocity at this point at t equals 1.5 seconds is going to be 0.300 meters per second. That means I'm almost stopping. But I'm still barely climbing. And so if you look at the time, I add on to my old table here, 1.50 seconds. I've only gone from 10.1 now to 11.48. So I'm really slowing down in this interval. And my velocity now is barely even moving. I'm almost stopped. All right? Now let's consider one more data point. And then really the point of this is to kind of show you how bodies change in time. So the last data point is I'm letting t equal 2 seconds. Y is v naught t minus 1/2 gt squared. Y is going to be 15.0 meters per second times 2.0 seconds minus 1/2 times 9.80 meters per second squared times 2.00 seconds squared. Again, be sure you square this time. That's 4 times 9.8 times -0.5. Okay, so understand how to do that. Y at t equal 2.00 seconds then becomes, it's very interesting, 10.4 meters, and the velocity is v naught minus gt. The velocity v equals 15.0 meters per second minus 9.80 meters per second squared times 2.00 seconds. I find out something very curious about my velocity, that it is negative 4.60 meters per second. Very interesting data point. When I consider 2.0, what has happened is I have reached the pinnacle and I'm coming back down. Notice I'm 11.48. I'm down at 10.4 now. Now I am falling. And an indication I'm falling is that velocity has changed sign on. So negative 4.60. So notice that initially you're rising as fast as you possibly can. Your initial velocity is totally positive, 15. As you increase in time, you're gradually not achieving as much height per half second. And eventually, and again, you're also reducing your velocity. Eventually, you get to 0 at the very top of your pinnacle. And you reverse and you start coming back down. All of that is wrapped up in these kinematic equations. All that behavior of a falling body is entirely captured in these kinematic equations by Galileo. Okay, so Galileo understood all of this. Okay? So, that's problem 1. Let me look at the next problem. Again, actually, this is problem 2.41 of open stacks. Again, that was 2.41. All right, I'm going to go now to open stacks. And I'm going to look at 2.44. Again, this is chapter 2, problem 44. And what's it going to say? It's a rescue helicopter. Okay, is hovering over a person. Whose boat has sunk. All right. One of the rescuers throws a life preserver. To the victim with an initial velocity of 1.40 meters per second. And observes that it takes 1.8 seconds to reach the water. All right. We want A. Okay, A says list the unknowns or the variables of the problem. We'll kind of do that as we do the problem. So, how high above the water was the preserver released? Okay, so this is only one. There's two parts of this, but I'm only going to do one part. So, how high above the water was the preserver released? All right, so a rescue helicopter is hovering over a person whose boat has sunk. One of the rescuers throws a life preserver to the victim with an initial velocity of 1.40 meters per second. He's not just dropping it, he's throwing it. Throwing down 1.40 meters per second. And observes that it takes 1.80 seconds to reach the water. How high above the water was the preserver released? So again, what are we looking at? We're looking at straight down motion. So you have initial velocity v naught. That's basically a 1.40 meters per second coming down, and that preserver is going to come down and hit the water, and this whole process is going to take a time 1.8 seconds. Okay, so that's what's happening. We know the initial velocity, we know the time, and we know how long it's going to take to occur. Okay, and so I'm going to erase the board so I can do the problem. All right, so again, hopefully you have everything. This is OpenStax 2.44. That means go to the OpenStax book, and I'm basically taking problem 44 out of chapter 2. Okay, so what is it that we know? Well, we know that everything is going downward. So, as I said in the chapter 1 lecture, we humans, we're just observers. We can choose a coordinate system that's most beneficial to us. Why not make the y-axis positive down? All the motion's going down. So let's choose a coordinate system where the y-axis, what we define as positive, let's call it upside down. Let's say that upside down is positive. That's nice because all my variables are heading downward, and gravity now becomes positive in my equation. All right? And so now what do I know? Again, that may seem weird at first, but again, why pick a coordinate system that's just difficult for us? Why pick something that's going to have extra negative signs floating around? Let's not do that to ourselves. All right? And so what I know is V naught is 1.40 meters per second. And I know that the time of fall is going to be 1.8 seconds. What I don't know is what I'm being asked is what is y minus y naught? That's what I don't know. And I could call y naught 0 for convenience. It doesn't really matter. So what I have to go do is I have to say, well, so first of all, what am I looking for, and what's a good equation to use? Now again, I'm hoping you wrote down the list, the toolbox of kinematic equations. I don't have enough room to. Usually when I'm teaching, I just stick them in. I have a big white whiteboard, and I kind of just put them on the side, and we point at them, right? So if you look at your toolbox and you look at of your kinematic equations, you need to have one that has y minus y naught in it, and you know absolutely nothing about the final velocity. It doesn't tell you what the final velocity is. And so if you look at that catalog of 4 equations, the one that wins is this one. Y minus y naught is v naught t plus 1/2 gt squared. And you say, well, you wrote down minus. Well, yes, I wrote down minus originally because I had a right side up positive coordinate system. But now my coordinate system is upside down, which basically means that g works in the positive direction. Hence, that becomes a positive value. All right, and so I'm looking for y minus y naught. So I don't have to do any algebra. There's no algebra necessary. And so what I'm going to do is I'm going to say, well, Normally, there's algebra that has to be done to solve for the variable, but it's pretty much we're looking for what's already written. The equation's written for it in the first place. So all I got to do is plug in numbers. So y minus y naught is, again, v naught is initially down, but that's considered positive. Remember, down is positive, g is positive. So it's going to be 1.40 meters per second. And it says it takes 1.8 seconds for this to occur, plus 1/2, 9.80 meters per second squared times 1.8 seconds quantity squared. If I do all of this, I will find out that the helicopter has a displacement, the displacement of the life preserver being dropped, or how high the helicopter is above the water, basically it ends up being the same thing. We find out that's going to be 18.4 meters. So when I say show your work, what I mean is I want you to define the variables, draw a little picture, state what equation you're going to use, do whatever algebra is necessary. When you get down to the bottom, plug in the variables, and give me the final answer with a box around it. That's showing your work. Okay? All right, so I'm going to erase this. And we'll do another problem. So all I'm doing for the rest of this video is just a few problems. So I'm going to do one that's a little bit harder. Let me take a swig of my water first. Okay. I'm going to look at OpenStax 2.46. All right, so writing this out, it says a swimmer bounces straight up from a diving board. And falls feet first into a pool. She starts with a velocity of 4.00 meters per second. So that means she's going to start going up. And her takeoff point is 1.80 meters. Above the pool. All right. A, how long are her feet in the air? So again, we're going to look at her feet because really where her feet touch the water is where the problem is eventually over. And so the question is, you know, she's going to leave the diving board. How high do her feet get, and then then when her feet touch the ground. So that's what we're going to focus on in this problem. And so let's see, how long are her feet in the air? First thing I want to understand. B is, what is her highest point above the board? All right? And then C, what is her velocity when her feet hit the water? Okay, so 3 things to find out. So a swimmer bounces straight up from a diving board and falls feet first into a pool. She starts with a velocity of 4.00 meters per second. Her takeoff point is 1.80 meters above the pool. A, how long are her feet in the air? B, what is her highest point above the board? C, what is her velocity when her feet hit the water? Okay, all of that. So I hope you have that copied down. I'm going to erase it all so I can actually do the problem. All right, so again, there it is. That's the problem. Now let's go do it. So keep in mind here my definition of variables. And so since she's going to go up and down, we might as well just have a positive y-axis up, right? I mean, I picked a positive y down because all my motion was going down last time. But she's going up and then down, so there's no real advantage to that. And so what we're going to do is we're going to call this a positive y-axis. And we're going to assume here now we happen to know what her y-naught is, right? It says she starts off 1.8 meters above the ground. So that's her y-naught. Or 1.80 meters. She starts, if you read carefully, she starts 1.80 meters above the pool. So that's her starting point. So here's the level of the pool. This is y equals 0 down here. And so she's 1.8 meters above the pool when she first gets going. Her initial velocity is going to be essentially, when she jumps off the diving board, and it's going to be in a positive direction. So we also know that her initial velocity is 4.00 meters per second. Again, that's going to be up, positive. She's initially jumping up. And we want to find out how long is she in the air. So the question really comes down is that she's going to start off at y equals y0. She's going to jump, and as we saw in the first problem, she's going to slow down and slow down. Eventually, she'll get to the highest point where her velocity is 0. Then she'll start falling back into the water. And the question is, when she hits the water, her feet are going to be at where? Y equals 0. So the question we want to ask is, at what time is y equal to 0? That will be the time how long she's in the air. All right? And so we're going to take a look at the equation y minus y0 is v0 t minus 1/2 gt squared. That's the equation we want to use. Again, we don't know anything at all about the final velocity, and we're interested. We really know that we know the displacement information. We know v0. We're asking about the time, and of course, g is not a variable anymore. I mean, the acceleration is not a variable. We're talking about free fall, so g is actually a constant. All right, so we have a little bit of work to do. And so first and foremost, we're asking, we want the final y to be 0. We're basically saying we want to know what t is y0. That's what we want to know. We're going to set y equal to 0 right now because that's what we're asking. We want to know when her feet hit y equals 0. She's going to go up and then come right back down. And then that, when she hits y equals 0, the corresponding time will be how long she was in the air. All right, so we can look at this and say, okay, well, we have negative y0 equals v0 t minus 1/2 gt squared. Now, here's the unfortunate thing. The variable that I want to solve happens to be wrapped up in a quadratic. I actually have to solve a quadratic equation. So let's set it up. So let's kind of throw everything, let's kind of set up a basic quadratic equation. I'll kind of review algebra for a moment. So I'm going to throw all the variables on their side. So I'm going to add 1/2 gt squared to each side and subtract v naught t to each side. If I do that, I find out that I will have 1/2 gt squared minus v naught t minus y naught equal to 0. All I've done is I put 1/2 gt squared on the other side, and I subtracted v naught t on the other side. Now, remember a quadratic equation back from algebra. Remember that? It was, again, I'm going to go back to algebra units. Remember we had ax squared plus bx plus c equals 0, right? Well, this is my a, 1/2 g. This is my b is negative v naught. My c is negative y naught. Remember we had a ready-made formula for this, right? We called it the quadratic equation. Or quadratic formula, I should say. Remember, it's kind of an ugly-looking thing. It was that I want to find x. X is wrapped up in a quadratic. It's going to be negative b plus or minus the square roots of b squared minus 4ac. And again, that's under a radical. And all of this is divided by 2a. Remember this formula? So again, it's negative b. Again, that coefficient. Plus or minus. There's going to be two answers, two possible roots to this. Square root of b squared minus 4ac. Again, the b squared minus 4ac is inside the radical. And then we divide entirely by 2a. Okay? So we've set this equation up. Our x is t now. That's our variable. We set this equation up to look like the quadratic formula. My a is 1/2 g. My b is negative v naught. And my c is negative y naught. I have basically the isomorphic formula. I have the quadratic formula written in this for this problem. So I can use the exact same equation for it. So I'm going to erase this algebra 1 stuff. And I'm going to essentially write out the quadratic formula. I need to use it for this problem. So I want to find the t. What do? Well, it's negative b. Okay, so that's negative of negative v naught. Be very careful with your negative signs. Plus or minus the square root of b squared. That's, in my language, that's negative v naught quantity squared. Minus 4, what is a? A is 1/2 g. What is c? Is negative y naught. So you got a negative sign craziness going on here, so you got to be really careful. This is all under a radical, and all of this is divided by 2a. What's a? 1/2 g. Okay? So that's what you have. Negative b, negative v naught, negative v naught, plus or minus the square root of b squared, which is negative v naught quantity squared, minus 4, a is 1/2 g, c is negative y naught. Again, that's all divided by 2a, and again, remember, a is 1/2 g in this particular formula. So what I'm going to do is I'm going to basically simplify things a little bit. And I've really solved for t. Okay, so I'm just going to rewrite this and simplify a little bit. So I know that negative of negative v naught is just v naught. So t is equal to v naught plus or minus. Okay, negative v naught quantity squared as well. Anything squared is positive. So v naught squared minus 4. We got negative times a negative is a positive. So this whole second term is positive. 4 divided by 2 is 2. So I have plus 2g y naught. And of course, on the bottom, 2 divided by 2 is 1, so I have just g in the bottom. All right, it's as simple as I could possibly write it now. Now, it's just a point of essentially plugging in variables. So I'm going to erase this stuff now. So, on so doing, T is, okay, V naught, we know is 4.00 meters per second, plus or minus, we have 4.00 meters per second, quantity squared, plus 2 times 9.80 meters per second squared, times the y naught is 1.80 meters. All right, all of this is under the radical, and I'm dividing everything by g. So my answer is going to, if I did everything in SI like I did, my answer is going to be in time. So this is what's interesting here. I will find out that I get something like this. I have 4.00 plus or minus. We work all this stuff out, you get 7.16. That's all divided by 9.80. Well, we now have to, oftentimes if you remember back in your quadratic formula, sometimes you get a value that doesn't make any sense. It's unphysical. Well, it makes no sense for time to ever be negative. You cannot have a negative time. So we have two roots. There are two roots to this answer. We got the root with the plus and the root with the minus. So one answer is 4 plus 7.16 divided by 9.8, and the other answer is 4 minus 7.16 divided by 9.8. There are two answers that are possible. We want to throw away the one that's negative. If I go 4 minus 7.16, well, let's just do it. So I have two possible answers, right? If I add 4 plus 7.16 divided by 9.8, I'll get 1.14. If I do the minus, let's work this out, I get 4 minus 7.16 divided by 9.8. I get a oddball looking negative 0.322 seconds. This is unphysical. Time can't be negative. That means that my answer is she's in the air for 1.14 seconds. I mean, having a negative value for time makes absolutely no sense. We refer to that in physics as unphysical. All right? So that's how long she was in the air. 1.14 seconds. All right. And that's all I did is I just set y equal to 0. I want to find out when her feet were at the level of y equals 0. Okay? That's part A. Now, part B asks, what is her highest point above the board? Okay, so we can kind of remember this 1.14 seconds. I'm going to erase this now, and I'm going to do part B. That was part A. So part B said, what's her highest point above the board? Well, what that says is essentially one way to attack that problem is to essentially ask, well, when is her velocity equal to 0? Remember, at the highest point, of freefall, or at the pinnacle, as we would say, the velocity is 0. She temporarily stops. Okay, so she has her fastest, velocity initially off the board. She slows down, eventually stops momentarily with a 0 velocity, then she starts to fall and accelerates downward. So what the question then becomes is, well, we don't know, we're not being asked anything about time. So if I'm looking for, the variables, I want to be able to employ the fact that the velocity at the highest point is 0. But one of my equations that involves time, one of my equations that involves velocity also involves time. I'm not being asked anything at all about time. I need to have an equation that knows nothing about time. So out of my catalog, I will pick out this equation. V squared is V naught squared minus 2G y minus y naught. That's the equation I want. It knows nothing about time. And at the pinnacle, at the highest point, I know that the velocity at the highest point is 0. So I know that I'm being asked, essentially, what is the displacement that corresponds to her having a velocity of 0? That only occurs when she has that momentary point of rest at the top of the pinnacle, at the pinnacle of her motion. So I will set that equal to 0. And what I can now do is do some algebra. And so I'm going to basically put this whole term on the other side. I'll say, okay, I got 2G y minus y naught is equal to V naught squared. And I'll divide both sides by 2G. So y minus y naught is V naught squared over 2G. This is the displacement that corresponds to her having a 0 final velocity in her motion. She's going to have initial velocity, she's going to rise up, and she's going to have zero velocity at the top. This is the displacement that corresponds to that. All right, so what am I asked? What am I being asked? What I'm being asked is, for part B is, what is her highest point above the board? Not what is her highest point above the pool. What is her highest point above the board? That would be y minus y naught. If I wanted it above the pool, then I would just, I would then have to go and solve and make up the, basically add whatever this answer is, or basically take y naught away. So if I want the answer, so essentially, what I want is her highest point above the pool. That would be her displacement. So essentially, I'm ready to go. So y minus y naught is the 4.00 meters per second quantity squared divided by 2 divided by 9.80 meters per second squared. All right? And when I do all of that, I will find out that y minus y naught is going to equal, again, let me write this over here off the camera. Okay, again, this is going to be 4.00 meters per second quantity squared divided by 2 divided by 9.80 meters per second squared. If I take 16, which is 4 squared, divided by 2 divided by 9.8, I will find out that y minus y naught equals 0.816 meters. Again, that is her highest point above the board. Not above the pool, above the board. That's the displacement from her initial position. Okay, one more problem to do in this, and that is we want to find out what is her velocity when her feet hit the water. Now, what's nice is that I can actually now use a previous result to help me do this. All right, so I'm going to erase this now. I want to find out what her final velocity is before she hits the water. Well, what does that mean in other words? So part C says I want to find V when her final velocity, when her feet strike the water. Well, what about this? I really want to find V for t equal total time, which I calculated in part A, right? And so I really want V for t equals, remember, go back to part A, how long was she in the air? 1.14 seconds. I really want to find out what her velocity is when she was basically about to hit the water. That's another way of looking at this. And I'm basically nicely using a previous result. I did all the work, so why not reuse it? That's fine. And so what I can do is I can use a nice easy equation. V is V naught minus GT, where I want to use this T. So V is, her initial velocity is 4.00 meters per second up, minus 9.80 meters per second squared, times this 1.14 seconds. Finally, I will get that she will have a final velocity of negative 7.17 meters per second. Or we can think of this as 7.17 meters per second down. The negative means she's falling. Okay? So again, that's what this problem is. It's a whole lot of stuff involved. And again, what I've had to do is I've had to select equations based upon what I know and what I need to find out. And so again, in the catalog of equations to choose from, sometimes I have to do that. Okay, I'm going to do, I know I'm running kind of long here. I like to do, I like to actually do 3 more interesting problems. So if you bear with me, again, all I'm going to do from the rest of this video is I'm just going to do 3 more problems. I think these problems are helpful to you. And they're all very interesting. And of course, I find all physics problems interesting. So, with that said, 3 more problems, so we're done. All right. And so I want to look at OpenStax 2.49. And I always find doing physics problems fun. So, all right, you throw a ball. Okay, straight up with initial velocity at 15 meters per second. All right, it passes a tree branch. On the way up. At a height of 7.00 meters. How much additional time will pass before the ball passes the tree branch on the way back down? All right, so again, you throw a ball straight up with an initial velocity of 50.0 meters per second. It passes a tree branch, so it comes up, passes a tree branch, and it comes back down, passes the tree branch again, right? And so it says that passes the tree branch on the way up at a height of 7 meters. So the tree branch is 7 meters above the ground. You're going to call the ground y equals 0. How much time, additional time, will pass before the ball comes back and passes the tree branch on the way back down? Okay, that's what we're being asked. So it's a very interesting, cool problem. And we're going to find out that we're going to end up using the quadratic formula. But this time, both solutions will be okay. the first solution will be the time that the ball heads up, and the second solution will be the time that the ball comes back down. All right, so let's see how this works. I'm gonna erase this. Again, you look up your. I'll give you the link to OpenStax. I've been meaning to do that, and I've been busy. All right, so what's our problem here? Well, we're gonna have the ball. We're gonna say that ball's gonna get thrown from y equals 0. The ball. Again, we're gonna have a positive y-axis up because why? Because the ball's gonna go up and down, just like the swimmer. So there's not, just straight down direction. So there's no advantage of me having an upside down y-axis, right? So I might as well just keep it up. So here we have y up, and then there's going to be a y max up here, whatever that is, and somewhere along the line is the tree branch, and we'll call that y1. 7.00 meters. So again, the ball is going to have initial velocity right down here, v naught, and it's going to go up past the tree branch, go to a maximum pinnacle value, stop momentarily, come back down, past the tree branch again, come back down, hit the ground. All right? All right, so we want to know, so we're going to let y naught equal to 0. So y naught is going to equal 0. We're going to say that the initial position is 0. We're free to do that. We can define that as 0. And so the question is, we want to find out at what times y equals y1. So we're going to use the formula that we've seen before. So y minus y naught is v naught t minus 1/2 gt squared. Again, what we want to do is we want to dress it up a little bit, basically fix it for this problem. We want to say, well, we're going to consider y naught to be 0. We're going to define the ground as 0. And we want to basically say, we want to know at what times that y is equal to y1. So there's going to be 2 solutions to this, right? So it's going to be y equals y1 at v naught t1 minus 1/2 gt1 squared. So at times, and I say times plural, at times t1, the object will be the ball will be at a height y1. And so I'll actually get 2 solutions to this question, 2 solutions, and they're both going to be valid. Neither one of them will be unphysical. All right, so that's kind of one of the cool things about this problem. So the uncool thing about this problem is I have to use a quadratic formula. All right, so let's set it up, look like a quadratic again. So I'm going to throw everything on one side. So I'm going to add 1/2 gt1 squared on both sides, subtract v naught t1 on each side, and I'm going to rewrite this equation as 1/2 gt1 squared minus v naught t1 plus y1 equals 0. So again, I threw the 1/2 gt1 squared on one side, I subtract both sides by v naught t1, I left y1 alone, and I basically threw everything on one side and left 0 on the right side. That's all I did. And now, unfortunately, we got to use the quadratic formula, right? So again, I showed you the quadratic formula last time. So I'm solving for t1. And again, it's negative b. Again, this is my a is 1/2 g. My b is negative v naught. My c is positive y1. All right, so negative b is negative of negative v naught. Be very careful of the negative sign, so mess you up in a minute. So negative b plus or minus the square root. Again, we'll put the square root last. We're going to have b squared. That'll be negative v naught squared. Make sure that you square everything. Don't just put the negative on the outside. You want to square negative v naught. That's what needs to get squared. Okay. A lot of students make that mistake. So let's see. Negative b squared minus 4a is 1/2 g. That's the coefficient on the square term. And then C in the usual quadratic formula, again, look back at your notes, one problem, is y1. Okay, we know y1, it's 7. I'm just going to keep these variables. All right, radical. And divide everything by 2 times 1/2 g. Again, that's 2a. All right? There's a lot of similarities between this problem and the last problem. So there it is, quadratic formula in its full glory. All right? So I'm going to go and erase all of this stuff. And I'm going to kind of just, this is the algebra portion of it, right? I mean, showing your work. What did I do? I stated my givens, drew a picture. I wrote down the equation I'm going to go use from the Kinematic Equations. I did the necessary algebra. I'm going to simplify the algebra one step, and then I'm going to put numbers in and solve it, and then give my answer. Okay, again, that's showing your work. So we can simplify this like last time. T1 is negative of negative V naught is V naught, plus or minus two solutions. Negative V naught quantity squared, I might as well just call it V naught squared. A square is always positive. Now, I have minus, right, so I have 4 divided by 2 is 2. So negative 2gy1. That's what this second term over here in the radical gives me. Square root of all that stuff. And on the bottom, I have 2 divided by 2. That's 1. On the bottom, it's literally just g. All right, so I'm about as simplified as I can possibly get. Doesn't look too simple, but that's the way it is sometimes. All right, so now I'm going to go in, put numbers in. So T1 is V naught. Okay, so what do we say that V naught was? I think it was 15. Double check that. Yeah, it's 15 meters per second. Plus or minus. Okay, square root. 15.0 meters per second. Quantity squared. Minus 2, 9.80 meters per second squared times 7 meters. Let me write this better. T1 is 15.0 meters per second plus or minus square root 15.0 meters per second quantity squared minus 2 times 9.80 meters per second squared times the height of the tree branch above the ground, 7.00 meters. That's all of this is under a radical. Everything is divided by g. 9.80 meters per second squared. So all of this should be, everything being an SI, I should have a time for everything, right? So I will find out that, I'm going to have 15 squared is 225, minus 2 times 9.8 times 7, and you work all this stuff out, you find out that you got 15.0 plus or minus, so you work all this stuff out inside the radical, called the radicand. You take the square root of all of that, and when you do that, you will find out that you have 15 plus or minus 9.37 divided by 9.80. And all that's going to be seconds. So both of these terms are okay. Because if I do the plus on top, if I say, one of my solutions is 15 plus 9.37 divided by 9.8, that solution, let me do the minus first, 15 minus 9.37 divided by 9.8. If I do that solution, I get 0.574 seconds. That's the minus solution. And I can say, and the other solution would be 15 plus 9.37, that whole denominator, the whole numerator divided by 9.8. If I do that one, I get a bigger answer. That's 2.49 seconds. That means that in this problem, if I'm looking at my stopwatch, as time it passes the tree branch the first time in only 0.574 seconds. Goes all the way back up, and when it comes back down, it's been in the air for 2.49 seconds by the time it passes the tree branch on its way back down. But that's not exactly what